In this video, we're going to return to something we did earlier in the year, that is finding the derivative of inverse functions. Earlier in the year, we did this with inverse trig functions, and we did it to find the derivative of the log function, which is the inverse of the exponential function. Now we're going to go back and do exactly the same thing. We're just going to pay attention to the fact that we can do this in general for any function which has an inverse. So if we the problem as stated here is find an equation of the line tangent to G at the point AB. We've got that diagrammed here. If we have an equation for F, so we don't have an equation for G, we have an equation for F, but we know that G and F are inverse functions. So that means we know that G of F of X is going to be equal to X. All right. And let's just come over here for a second and notice that if AB is on G, then we know that BA is on its inverse, F. BA is on F. And if BA is on F, that means that A is equal to F of B. That'll be useful in this problem to think of it that way. So we want to find an equation of a tangent line, so we need a point, which we have. We need a slope, which we're going to need to find. We need G prime of A. It is going to be helpful to realize that A is F of B, as we just said. So another way to think of this would be G prime of F of B, which is not as pretty as G prime of A, but it's equivalent to it. All right. So using this relationship between inverse functions, we're going to do implicit differentiation here to find G prime. So d dx of G of F of X is G prime of F of X times F prime of X. And d dx of X is just 1. So we get G prime of F of X is equal to 1 over F prime of X. So the derivative of G at F of X, so that's at the output of X or the input of G, so G prime of F of B, or, as we said above, G prime of A, is equal to 1 over F prime of whatever that X was, that was B, 1 over F prime of B. So G prime of A is the reciprocal of F prime of the y-coordinate B. So our equation of the tangent line in green up there is just going to be y minus the y-coordinate equals the slope, which we've just determined is 1 over the derivative of f evaluated at that y-coordinate times x minus a. Alrighty, and we'll just look at that now in a specific case. So let's scroll on over here and find an equation of the line tangent to F inverse at the point 1, 2, whoops, if F of X is equal to that big mess. So one question actually is whether we're sure that has an inverse. We'll come back to that question in a minute, but for right now, let's just assume that it has an inverse and try to find the equation of the line tangent. So we'll just, instead of remembering the result from last time, let's just rework it out. We know that F inverse, let's call it G, so we don't have to keep writing that -1. So G of F of X, we know if they're inverses, is going to be equal to X. And when I take the derivative of both sides, I get G prime of F of X times F prime of X equals 1. So G prime of F of X equals 1 over F prime of X. Okay. F of X, remember, is the A. The output of F is the input of G. And the input of F is the output of G. So that's A equals 1 here. This is, the input was B. That equals 2. So we've got G prime of 1 is going to be 1 over F prime of 2. Okay, and after you've done this a few times, you don't have to rederive it every time, but if you forget, it's not hard to rederive. If I want G prime at a given X value, I do 1 over its inverse at the corresponding Y value. So now I actually need to find F prime in this case. F prime of X equals 3/8 X squared plus 1/4 the natural log of X minus 1, 1 over X minus 1. Technically we need a chain rule here, but the derivative of that baby is just 1. And we needed F prime of 2, the Y value. F prime of 2 is 3/8 times 4 plus 1/4 times 1 over 1. F prime of 2 equals 3/2 plus 1/4. 3/2 is 6/4, so that's 7/4. So F prime of 2 is 7/4. G prime of 1 is 1 over that value, so G prime of 1 is 4/7. So the equation of my line tangent to the graph at 1, 2 is Y minus 2 equals 4/7 times X minus 1. And I have that here for us on Desmos, so we could take a look. Oops. Let's just zoom this aside for a minute. And let's put this equation where we can see it. And here we have graphed F. That's the red function. The blue function is symmetric to F around the line y equals x. We had the point 1, 2 on our blue function. That's F inverse. And we came up with the equation y minus 2 equals 4/7 times x minus 1. Look at that. There is the equation of the tangent line. All right, so the only thing left to do is talk about this question that I raised briefly right before we solved that problem. which was how do we guarantee that the function has an inverse? So remember that in order for a function has to have an inverse, it's got to pass the horizontal line test. There has to be just one y value for every x value. And if a function is always increasing or always decreasing, that will be true. If a function changes from increasing to decreasing, it will not have an inverse over its entire domain. You could restrict the domain and find inverses of parts of it. But you might be asked to prove that a function has an inverse. All that you have to do then is to prove that it's always positive, that its derivative is always positive or always negative. So in this particular case, when I did f prime of x, I got that expression. Note that 3/8 x squared is always positive. Now x minus 1, the other place an x shows up, could be negative if x is smaller than 1, but in this case our function didn't have the domain of our given function was only numbers 1 or larger because we were taking the natural log of x minus 1. So this term is also positive for all x in the domain of f. So we have a positive number plus a positive number. The sum of two positives is always positive. Sum of two positives is positive. So f prime is greater than 0 for all numbers in the domain of f. Therefore, f inverse exists. So that's just another little piece it's possible you would be asked to do sometime, is to use this sign of the derivative to show that the function has an inverse.